Bonjour à tous, bienvenue à ce webinaire Uranus qui sera présenté aujourd'hui par Martin Larson. Puisque Martin est un chercheur au Danemark, je vais faire les introductions d'usage en anglais. So I'm going to switch to English now. So first of all, thank you, Martin, for accepting to present at the Uranus webinar. So Martin obtained his PhD in 2013 from the University of Copenhagen, working on dynamically coupled hydrology, land surface regional climate model simulations. He then went to work at the Technical University of Denmark, where he's been for 10 years, a bit more than 10 years, doing mainly modeling and statically based climate change impacts within floods, socioeconomic damage, cost, and the water energy nexus. He's currently working as a senior researcher and had two research groups, the Regional Ocean Modeling Team and the Precipitation Radar Team at the Weather Research Department of the Danish Meteorological Institute, where these research teams conduct basic research alongside model development within models that operate 24/7 for both forecasting and warning purposes. He's also a member of the scientific steering group of the newly formed risks from the WCRP. And it's within this context that I met Martin last fall in Barcelona. So through a conversation, I realized that he was working on things that we were also working here at Uranus. And one of these things was compound events, flooding events, to be more precise. So the coastal communities that are located near river outlets can be at risk of flooding both from high river stream flow and also high coastal water level. And studies have shown that if you neglect the interdependency between the two flood drivers, you actually underestimate the risk of flooding. So basically, if you assume that the frequency of high water level and high river flow are uncorrelated, you actually underestimated the risk of flooding for these locations. So we were working on this at Uranus for the St. Lawrence River, trying to estimate how much we're underestimating the risk by not taking this correlation into account. We have a study that's currently under review in Earth Future, and it's not what we're going to be talking about today. But just to set the context on why I invited Martin to present here, because he was working on something very similar in Denmark, and I thought it would be very interesting to get the Danish perspective on this. So before we start, just want to please remind you to mute your microphone if it's not already done. The presentation is recorded. And Martin asked that if you have any question during the presentation, don't hesitate to just raise your hand, and he said he can see it, so he'll take the question right away instead of just waiting for the end of the presentation. So on this, I will just pass it to Martin and catch you at the end.
Okay, thank you very much, Louis-Philippe. I hope you can hear me, otherwise let me know. You already introduced me. We talked about this compound study in Barcelona, that's true, and I will talk about a number of studies that I have been involved in the previous years, all somehow related to compounds. Just a brief presentation of me. As I said, you already did it. Maybe I could add that, of course, being now in a med office in comparison to a university, I also have quite some cases that are politically sensitive, and I will also touch upon these. It's obvious when we do things related to the green transition and when we do things related to big hazards where we have economics and potential damages and money at stake, then it becomes quite political. So that's, of course, also a part of my job, and I also manage the people, not just in terms of research, but also in terms of HR. And then, yeah, I think that's the additions to the presentation of me. And I will jump straight to the outline. And as Louis-Philippe also said, please ask questions along the way. Right now, I actually don't know how many I'm speaking to, and I can only see a matrix of black screens. Having taught at the university during Corona, this could be a little bit, as a remote, strange, lonely feeling. So please speak up and maybe even open your camera so I can see, because I have like a screen to my right as opposed to your screen, so I can actually see some of you. It's also completely okay if you don't. It was just a suggestion, so it's a bit more personal and interactive. Thanks a lot. I can see some of you now. That's good. So this is the outline. I will start by presenting a study we did on extreme storm surges for Greater Copenhagen. It was just finished, and that was very politically sensitive. Then I will jump into compounds in an operational context for DMI, and then present a new project we just got funded, and then previous compound studies with different aspects. So in the presentation of me, you could see that if you know at least some of these affiliations, that I have been located in Copenhagen more or less all of my life. I'm also born and raised in Copenhagen, and Copenhagen is a capital region of 1.5 million citizens, being very exposed to floods. We have a lot of coastline in Denmark, and Copenhagen is no exception. And in Denmark, we have this public climate service tool where you can pull a slider, as you can see I did here on the top, and then you can see the resulting flood from the sea, storm surges, assuming a static flood, meaning a really long duration flood, of course. And you can see the resulting flood here for storm surges of 3.9 and 5 meters. And that sounds really high, but it's actually not by coincidence that I chose these rises in sea level. And I will get back to that. So this is sort of one intro to this study. Another intro is that the current coastal protection in Copenhagen is really fragmented, and it's also quite uncoordinated, because even within this coastal stretch you see here, the outer line is around 65 kilometers long. There are 4 municipalities on the coastline, and their efforts to adapt is quite sort of uncoordinated and also politically bound, with different parties being in the local parliament. So it needs updating. And talking about Copenhagen, you could not have located a capital region in a more complex setting. That's at least my statement. So this study shows the most sensitive wind directions forming the highest storm surge levels across the Danish coastlines. And we have, I think the most recent update is 8,000 kilometers of coastline. Of course, it depends on the scale you look at, but you can see that the most sensitive wind direction for different parts of Denmark and even around Greater Copenhagen is very, very different and varying. This is using artificial winds in a model study. And the reason it is like this, even around Copenhagen, is because the greatest storm surges for Copenhagen, for southern Copenhagen, comes from the Baltic Sea, which is to the east of this map. I don't know how familiar you are with this geography. Maybe I should have made a larger map. That will come later. And for northern Copenhagen, the highest storm surges come from the north. So there's a lot of variation here, and you cannot really see that in the storm surge statistics. So these recurrence levels, meaning how often do a certain water level occur historically, it looks quite similar whether you look at Copenhagen North, that's on the left, or Copenhagen South, that's on the right. But that's because we had different occurrences of historic observations in these underlying statistics. So if you include much earlier recordings, going back to pre-medieval times, the earliest is from 1044. Some studies have tried to reconstruct using such observations. Then you get another type of statistics. And mind you that some of these recordings, they are marks on old church doors and eyesights, and they are even located in Germany and have been sort of moved, relocated to Danish conditions. So there's a lot of uncertainty within these results. So comparing the official statistics to the left with a newer updated statistics from consultancy companies on the right, you get very, very different statistics. These don't have the same axis, but when I zoom in, you can see that the axis, that the results and the underlying statistics is quite dissimilar. So for example, a 1,000-year return period, which you see in the x-axis, is more than double using these previous recordings compared to the official recordings. And that's especially related to some really high events occurring also in the 1800s, especially a high event in 1872, which itself was the reason why we started doing official recordings in Denmark. Okay, so this is you can say the basis for the adaptation solutions that the municipalities then have. So should they use the results on the left or the results on the right? This was their dilemma up until now, because now we did this study coming from the government where we tried to make a more authoritative estimation of these storm surge protection levels. And that's based on storm surge modeling using this 1872 storm. And now you're maybe wondering, how does this relate to compounds? It's basically because storm surges can only be of this magnitude if you have a pre-filling of the Baltic Sea, which is a big inlet, as I said, to the east of Copenhagen. So we tried rerunning 1872 with different filling levels of the Baltic Sea, and also, of course, looking at the statistical occurrence and probability of this occurring. And we could find relations between the filling level and the resulting storm surge. So these are different filling levels at different sites. And we could actually make quite a simple algorithm where we calculate the resulting storm surge based on different filling levels, but also based on increasing wind conditions. It was a linear relationship. So we could actually, for this study, nitpick within such a table like this one and see, okay, we want this and this pre-filling level, and we want this and this increased wind speed. And in doing so, we tried to estimate what we call the physical maximum, which in itself is a peculiar sort of term, because we know, of course, as geoscientists, what is that, but that is related to also the tolerance levels of stakeholders, because they more or less said they have a zero tolerance. So for example, the metro company of Copenhagen was included in this study, and they said that if the metro gets flooded, then it's closed for 2 years. So they have a zero tolerance. They want a really, really, really conservative estimate. But of course, if we, on each assumption and each factor involved, took the most conservative bet, we would end up with adaptation levels of, I don't know, even 10 meters of storm surge. You can always increase. So this study was very much about also this two-way stakeholder interaction, and neighboring working groups were looking at adaptation options within this traditional cost-benefit approach, where you actually do need not the physical maximum, but return period levels. So another governmental authority called the Coastal Authority, here abbreviated into KDI, they were somewhat forced to look at this uncertainty span, you see, like this funnel shape, where they were then providing return period levels for, say, 1,000-year and 10,000-year return periods. We then also did some additional modeling. The initial study didn't include new modeling, but only previous modeling. So that was based on this study, which a PhD of mine did some years ago. But we were then told to do additional modeling because we wanted to more firmly establish the results. So what we did was, initially we of course reproduced the runs that this PhD did, but also did that based on additional subnesting of the storm surge model. You can see on the top right that we subnested around the region of Copenhagen. Here you can also see the entire extent of Northern Europe with the Baltic Sea to the right of Denmark, which is quite a mass of water to enter the Danish straits. We have these 3 straits where the water exits exits from the Baltic Sea. And we even tried doing model runs where we had down to, I think it was 37-meter resolution, resolving the inner channel in the Copenhagen harbor. But we ended up using the official storm surge model, which we use on an everyday basis to forecast and warn the Danish society through official outlets. And it was the official model, and it was well validated over several years. We also looked at the wave setup that's in the lower left, and then we firmly established this relationship, again, the compound angle between the filling level of the Baltic Sea and the resulting storm surges. We then looked at the historical wind speeds, many different data sets, reanalysis data and observation data, that's the column to the left. We also looked at the spatial distribution around Copenhagen, and we did so because we have a natural threshold between Denmark and Sweden. There's this strait called Øresund between Denmark and Sweden, which is around 20 kilometers wide. And there's a threshold here where the water does not pass. So that's also a part of the reasoning between these big differences in storm surges coming from the south and from the north. And one major finding that we did was that we then took the atmospheric forcing that we had for 1872, which is quite a famous data set in Northern Europe at least, where this 1872 storm has been reconstructed and put into GRIP or NetCDF file format so it can be used in different impact modeling. We took that data set and then we tried to vary the wind direction for that data set in increments of 5 degrees, knowing, of course, that we then break down physics a little bit. So we didn't do it all the way around 360 degrees. We just did it plus minus 15 degrees. But in trying to, in a simple manner for this study, implement what would happen if the storm track had been different. And that actually caused further increases of this storm surge, forcing more water towards Copenhagen compared to other regions in Denmark. And that resulted in these results. So we divided the coastline into north, that's the top row, and an intermediate region, that's the middle row, and a south coastline, that's the bottom. And then going 50 and 100 years into the future, we then had storm surge levels of between around 4 and 5 meters for now and the future for the southern part. And that should be compared to levels of around 6 to 7 meters from previous consultancy reports. So we did actually lower the resulting storm surges quite a lot compared to the consultancy reports, but it was still much higher than the official return period statistics, which does not include these extreme events. I think the next slide is from the next study. So maybe we should have a short stop and ask, do you have any questions now up until now? That's also completely fine. I will just continue then. But just raise your hand if you have questions or speak out loud. I will not read all of this, but now I will jump to what we do here at DMI, at least in my weather research department. So I'm heading 2 groups within the weather research department. And other than doing core research, we also are the model owners of and model developers of models that work on an operational basis, so 24/7. So we initiated a study where we tried to assess the feasibility in implementing compounds into our operational services. And this is sort of the draft idea for that study. So we wanted to provide a framework for how weather warning institutes can include compound events. For the purpose of our study, we needed to categorize types of floods that occur in Denmark. We often talk about floods, and I will often talk about floods. That is the main source of sort of damage and impact in a Danish setting. And also historically what has caused the highest damages. We don't have earthquakes, and storms cannot tip over anything here. So it is basically floods I will be talking about. Then we also assess the historical occurrence of DMI warnings. We send out warnings, and we try to assess how these relate to compound types, because sometimes they overlap in type, and maybe we need to update the categories. And then, of course, we want to propose modifications to the system. So one approach is to look at the current warnings. That's the ones we have on the left. They're in Danish. Maybe you can see what they are based on the symbols. But we also try to assess which compounds can actually, or which types of impacts can actually occur at the same time, having this compound nature. And we do that both by sort of category, but also by variable. So this is one example of trying to grasp this quite complex compound approach in an operational setting. And then we look at more specifically what leads into the types of what leads into the floods, but also the types of floods. So this is an initial sort of paper title and structure of these types of floods, but also the 10-year distribution of warnings by type of flood. Many of them are actually multi-warnings. At present, we don't have a modeling system that can actually, in a coupled manner, handle compound floods. And we actually had a compound flood in Denmark, for example, on January 3rd this year, where we had 142 centimeters of storm surge south of Copenhagen, which in itself would not cause flood, but because we had so much coming from the hydrological side, from inland, we had a quite severe flood in southern parts of Sealand, which is the island name where Copenhagen is located. So that was sort of aspects related to trying to implement compounds into the operational setting of DMI. I'm just looking at my clock here. Then I would mention this new project we have, which is called ECHO, funded by Northern European funding agencies. Again, we focus on floods. As always, compounds are very data heavy, so we need long time series. And here we are trying to distinguish between what I call driving variables. So that would be wind or rain, which respectively are the drivers for storm surges and hydrological floods, and which would come from reanalysis data or RCM data, or it could even be grid observation data. And that's very much applicable for such a study, because you have the distributed fashion and you can extend it towards all the project partners, which come from all of Northern Europe. So you can just select the domain based on that. But we would also like to look at impact variables, which is the point measurements themselves, so sea level and discharge. That's of course easier to interpret for impacts. And I will get back to this distinction between points and the larger scale. So one aspect of this study is that we want to have an input into the Danish climate atlas. So the climate atlas is a national climate service that we have in Denmark, where we basically provide end users and stakeholders with climate information based on typical IPCC codex approaches. We look at decadal scales, ensembles, robustness measures, and we interpret that in a Danish context, and then we put that into a climate atlas where on the municipal scale or the national scale you can enter a scenario and different metrics, and then you get some sort of output. And in doing so, we of course also need to include some sort of future scenario runs for such a study. So that would obviously be codex, also depending on the timing of the new codex runs. But in doing so, in conveying such complex matters to end users, and I have even tried, in discussions with like-minded researchers, it's very difficult actually to discuss these things about the compound nature. And one example that I typically use is this figure on the left. So this is the storm surge level or the water level basically in the x-axis, and then the discharge for some coastal river station on the left. And here I then show the compound recurrence level. So for these two levels to occur at the same time. And I do that by showing these two variables where I assume that they are independent. So I basically just multiply their probability, but I also use different cupola functions, which is a typical approach to this compound analysis, which alters the location of these ISO lines a little bit. And so we were discussing in project meetings, could you actually present such a figure towards a public audience? And I don't think it's the case. And I become more and more sure that it's the case that we cannot do that. So what we really need to do is to present, using a school book example, we need to present for them a protection level, for example, for a storm surge, just like we always do. And then all the complex calculations behind the storm surge, being compound or not, we just hide them away. We can always take the discussions, what has caused this storm surge, but it's very, very difficult. The reason why there are these red dots, that was in an effort trying to sort of say, okay, but could we then present this point on the curve towards the public? But that would already involve a decision taken from our side. Where do we locate this red dot? What about if the red dot was skewed a little bit to the left or right? That would entail quite big sort of impacts to the economics, for example, behind such dikes, and also the location of them, because are we protecting against backwater or storm surge water? Another metric that I think could easily be perceived by the public would be flood maps. And here we could actually make flood maps stemming from compounds along the vast Danish coastlines, where we have high seawater levels and then resulting stemming up water from the backwater in these rivers. I think that would be easier perceivable. So I would love to hear aspects from your side regarding how you deliver these messages and metrics and stories, maybe through actually storyline approaches towards your end users, not just the science community, but also the ones that are maybe trying to implement it in cities and so forth. I think, yeah, now I switch study again. Are there any questions to this? Maybe we could talk about metrics and messages towards end users and climate services.
Yeah, I maybe have a question.
Yeah.
So you're saying that presenting those joint probability distribution is too complex for end users, but do you think that's also the case for like the engineering community? Do you think it's still too complicated for them to grasp and use in their own work?
Maybe that's like an intermediate step in terms of this understanding. And I have actually mostly talked with other researchers or municipalities about this. And of course, there's a big difference here. So maybe engineers would fall in between. I'm not sure. It's also a very general sort of statement talking about all engineers in one go. Do you have any experience with such communication since you asked the question?
Yeah, well, partly because we have a project where we're also considering compound events, so similar to yours essentially, and we're asking ourselves the question, how do we convert that into information that can be used for risk assessments?
Yeah.
And so if I'm willing to tolerate risk of, for example, 1 in a 20 year, 1 in 50 years, I need somehow to combine the different factors that lead into the final risk, so the sea level surge, and I have to deal with this joint probability distribution in some way. So yeah, we face similar issues, and our guess for the moment was to assume that engineers would be able to grasp that we made hypotheses linking together two different climate factors to yield a unique probability distribution for the risk they need to consider in their design. But I'm happy to be shown wrong, and I'm really curious to know what your experience dealing with those communities to basically confirm that it's a fair hypothesis to make.
Just a quick response, and then I'll ask you, Susan. But for example, if I had a system where I could move this red dot as like a cursor following this ESO line, that is the top one is 1,000 year combined return period. The resulting adaptation needs in an urban environment would change by moving that cursor, because it would shift from coming from backwater to sea level water. So this, I guess, this is the complexity we're talking about. It would entail completely different adaptation measures depending on where in this space you look. I don't know if you have a comment, or Susan, you.
It's not about the modeling and compound modeling. We use it, but for sea level and waves only. And we have presented it to a manager for municipality, and it can be explained with 2 or 3 typical cases. They don't understand Copula and everything, but it could be that type of storm or another type of storm, and that can be understood. Not population, it's a more difficult question, but for managers, if you have 2 or 3 theoretical storms, it can be explained. But my question was really because you have 1,000 years of return period on all your slides from the beginning, and in Quebec we don't really manage with such not probable storms. We are more in the 120, 100, and I just want to know if Danish government is really using 1,000, or is it more something for research?
I think it's actually changing a little bit, and also it depends on the context. And then there's of course, we could also go into the question on future scenarios, because that also impacts a lot. Which RCP to choose and which percentile in the RCP to choose. But actually a lot of studies present the 10,000 year return period as sort of a probable upper max. But some municipalities only protect towards 100 year. So there are lots of different approaches to that.
Okay, thanks a lot.
But I could have easily included the 10,000 year here as well. It's just up in the yellow.
Yeah, we never go so far.
Okay, so now I will continue. I will show some results using the climax data, which I actually think has an origin in your department somehow, at least partly. I used that to assess winds, and that was also in the context of this preconditioning for the Copenhagen site. So here I used this full ensemble of 50 single-member RCMs, which are of course perturbed, looking at this period available from 1950 towards the end century, and it's then based on the RCP 8.5. And that's of course beneficial to look at natural variability, and also to have a much firmer grasp of the extreme outcomes. And in doing so, I looked at different sites in Denmark and trying to assess where all of these things occur. So I assessed different combinations of winds and wind speeds that have historically led to high water levels. And in doing so, I initially looked at the highest water levels at these locations. So these are for stations in and around Denmark, and then sorted for the highest event. And you can see on the x-axis, you don't need to look in detail, but you can see on the x-axis that for 0, that's the peak of the event. And then I looked at the wind speed and the wind direction prior to event, to the peak, trying to understand the nature of these extremes. What were the wind speeds? What were the wind directions which storms forced these extremes in and around these Danish sites? And as I said, it's a small country, but it's very complex, and it's very different conditions that lead to high water levels around Denmark. What I then did was I programmed my post-processing routine in order to search for cases similar to all of these historical conditions causing the high water levels. Essentially trying to get wiser on the extremes, but also trying to get wiser on, will we see an increase? Will the wind, because the wind is the driving variable, as I said previously. So will the winds increase in magnitude and in frequency? And what I found was, green is the reanalysis. This is shown by box plots, and blue is historical, and red is future. What I found was that there was a tendency to have neither an increase in magnitude or frequency in any of these outcomes. So the x-axis corresponds to different conditions that I have scanned for, and neither of these conditions actually resulted in particular increases. And this is also what we saw in this Copenhagen study that I just mentioned. Winds, it's not sort of the driver of the change that we're going to see. The rise in sea level itself is the only sort of impact we want to look at. And we also assess this specifically using Cortex data for the Copenhagen project. We could not see any trends. And the trends we could see, they were not statistically significant. And we assessed the entire ensemble across RCPs and model members and everything. So this was, I cannot see the top here because of this zoom bar, but one is frequency and the other is magnitude, and neither show a vast increase. What we could also see is that we could become much firmer in assessing the upper tail of these extremes, and actually see how far we are off when we then use these wind results in forcing a storm surge model. We could become much wiser in these recurrence levels for the upper case, because there's a high spread here. Okay, so new study, and this relates more. I tried to zoom in on the conversation we had, Louis Philippe. So now we are approaching the studies on streams and sea levels combined. So now there's a study for a small town in Denmark called Abordera. I think there's a population of 20,000 people. And here we look, it has experienced a lot of floods, even though it's quite a small stream. Even for Danish conditions, it has quite a lot of floods, and some of them are compounds. And then I looked at the compound occurrency of water level, that's the top row, and discharge, that's the bottom row. And then I used different cupulas, different types of cupulas to assess this outcome space and basically increase the data available to assess these compounds. Also analyzing for the best type of cupola to represent these data. And again, I did so with this type of compound return period, using sorting both for the peak water level and the corresponding discharge at the same time, and vice versa. I also assessed by looking at both annual maxima and peak over threshold, extreme sorting algorithms. And this is then the resulting flood. So we had actually a dynamic model that coupled numerically coupled the physics involved in both the hydrology model and the storm surge model. So now it's not static modeling, it's actually dynamic modeling with storm surge propagation over land. And we could then see the affected flooded area based on the land use types we had available. So permanent housing, summer housing, commercial housing, and so forth for this municipality, based on different combinations of compounds from either stream or sea. We then also assessed the damage costs. So this is the net present value for the bottom row is the town I showed, the upper row is another town. And we could actually see that it's the typically the smaller recurrence levels that cause the higher net present value in these cases. And it's very much related to, of course, how frequently they occur, which also calls for adaptation measures to be implemented anytime soon. And actually, while we did this study, one of the towns already were building and now initiated a pump that is able to pump, I think it's 8 cubic meters of water per second. So it's a really big pump for a small municipality. So they're now able to prevent this type of compound flooding up until this level, at least. They also built a wall. Yeah, I think that was the point here. This is then a comparison between different data sets, because we also had different underlying data sets. And one big conclusion here is, of course, that you need to work with the municipality to do such an analysis, because we based this study on data that we got from the municipality. So really local data, GIS vector data, where we could see even, the plot scale of individual housing. And then we used an EU generic data set on quite a coarse resolution, and we saw quite different results based on that. And that's, of course, also related to how we then economically classify these land surface types. So it's really, really sensitive to some of these things as compared to the geoscience behind the forcing of the impacts. We also did a similar study for all of Copenhagen, and we actually did this study. This was then using static storm surge modeling and without any river flow. But on the other hand, we actually did this study on the best possible grid we have in Denmark, which is 40 centimeters. So really, really, really fine scale. But here we just aggregate the results on municipal level because we want to avoid, of course, breaking GDPR rules. But we could show on a house level which houses were flooded. And then we used 2 different proxies for monetary assets, being historical insurance data that we got to force our economic model, but also sales prices. And of course, that creates a big difference in the damage costs across the country, because insurance levels, they don't vary, or at least we didn't have the data from insurance companies to vary that across the country, but we did, of course, for sales prices. So the sort of the roads along the richer regions, you could say the capital region of Denmark, for example, it really sticks out when we use sales prices, because that's where we have the expensive housing, of course. Now I switch study again. Now I'll go back to looking at compounds between. Were there any questions related to these damage costs? Maybe we should have a stop.
There was one question in the chat. I don't know, David, if you want to ask it.
Sure. I cannot see it. Could you?
Yeah.
Yeah, I was just wondering what discount rate you were using for the NPV calculations.
So we used the official Danish discount rate, which I think is 3.5 in the first period, and then decreases to 2 or 1.5. So that's like a trajectory it follows. Is that what you mean?
Yeah, well, I don't see how it would change over time, but if it's around 3%, that's an answer to my question. Thanks.
Yes. That's the official Danish approach. But that's what we use. I'm not an economist, so I can't dwell too much on them.
Just maybe a comment is that when there are social costs to hazards, I think there is a move toward higher discount rates to account for those.
Mm-hmm.
When it's purely economical, then yeah, I think 3% is close to the standard?
As far as I remember, it starts off at 3.5 and then drops.
Okay.
So that may be related to the social aspects. I then did the same study for rivers and sea level for all of Denmark, or at least all the stations where I could find sufficient data to do so. And this was under the underlying research sort of idea that, as I said many times already, the conditions are quite diverse across Denmark. So it's different storms that force, different types of floods across Denmark. So could I see any systematic behavior in the dependence between these two variables across Denmark? So these are the water level stations and the discharge stations that are then used for this study. They were combined in different ways when two stations were equally close to another station. They were combined in different ways, but they needed to be quite closely aligned to be combined in this study. And again, in doing so, I did it for block maxima, peak over threshold, and then doing it for one observation per year and 5 observations per year, which of course were also related to the length of the time series I had at hand. And my conclusion so far, and I would like to input, is that it's actually really, really hard to find any patterns that feed into an obvious research paper with an obvious conclusion. And I mean, of course, if you get no systematic behavior, that's also a conclusion. But it's actually quite hard to go about finding systematic behaviors in this. I could find some statistical significance, but it was also, and it also grouped sort of in regions, but it was also very much related to my way of sampling. So this is actually not published yet, but I would like to do it at some point. And this is, I think, the study we initially talked about, Louis-Philippe, where you asked me to present this, and I only have one slide on that. And this is looking at the town of Halmstad, which lies just opposite of Copenhagen, more or less. At least talking about Canadian distances, they are very, very close. Here we would maybe still think it's quite a drive. So here we reconstructed data using different approaches. So EHYPE, that's a hydrological model. We have observations, the one called prediction, that's machine learning methodology. And then we had quite different combined recurrence patterns for these 5 and 30-year return periods. And we could actually see that the choice of river discharge, depending on how the data set were derived, were sort of the main controlling factor in this normalized difference value between the outcome in the return periods, followed by the choice of copula and then sea level with the least importance. And I think I'm actually all the way through now, 10 minutes before time. So maybe we should have a discussion.
Thank you, Martin. If people have questions, I think you can just raise your hand. Just while people think about their question, I have a question for you. So just to follow up on what you're showing. So in the previous slide, you showed that, the technique that you use, whether you look like annual maximum or peak over threshold, you get very different answers. And here you show that, the choice of copula also has an impact. So how would you qualify the uncertainty relating to these analyses? Like, can you just comment on the uncertainty? Like if somebody, like a decision maker, comes to you and just say, like, I need a number for adaptation or for a decision, what do you tell them given all these uncertainty?
It's a good question. Do you have a suggestion yourself?
Okay, then maybe an easier question would be like, what is the main source of uncertainty given all of it? Is it like the, block maxima or peak over threshold, or is it the copula, or like what should be like the first area that should be tackled if we want to reduce this uncertainty? Or
I mean, of course, the first step would be to really look deeply into your results and try to find any outliers and inconsistencies, because such analysis, if you have some, could be just a single observation that basically controls the entire picture. So you really need to be careful of all the data points you have in the upper end, and more careful the higher you go. Be really critical into the sort of the trueness of such an observation. But after having done that, that's like a pre-assumption. You need to do that in every study, of course. After having done that, maybe one approach could be to basically visualize the uncertainty stemming from each contributor. Here we show the influence of copula selection. I think you would never towards a stakeholder show results from 20 different copulas. You would always try to pick the best one. Or maybe if you have two that are equally good, but for different reasons, maybe you would include those two. And then you could go back into then assessing how you reconstruct data if you did any reconstruction. Of course, copula itself is a reconstruction, but sometimes we also reconstruct. There's another paper I didn't show results from, reconstruct based on neighboring stations, which can be beneficial, but it's also a little bit dangerous. And also, of course, the machine learning approach. So I guess it's all about communication and trying to have this dialogue.
Thanks, Martin.
Mm-hmm.
Yeah, you guys are blessed with a lot of data, which is not something that we have just for us. It adds even another layer of difficulty.
Yeah.
Do we have a question for Martin?
I mean, I can go ahead, but I'd like others to have the chance to speak as well.
Nobody raised their hand, David, so you can go.
All right. I really like this. So one question I had, and it's more maybe conceptual or philosophical, is if you have vastly different adaptation options depending on which criteria dominates the event, is it a good basis for decision making to have this joint probability, or we should like compress the joint distribution into a univariate distribution to make a decision for like each independent axis? And yeah, that's my question essentially.
Yeah, I think that was also one of my points, that it's really about distilling messages. Not that we should omit all the thoughts and mindsets and theories going into the work, and that would probably be an appendix in some report that maybe 10% of end users would actually read all the way through. But I agree that it's really about distilling these things into messages and storylines that can be perceived. But Susan, you also mentioned this combined storm surge and waves, and you said you had, was it 3 different scenarios? Or
we explained that, yeah, just you can have a high sea level and small waves, and afterwards we have big waves and not. But it's all coastal problems, so we don't have study on river now. We have problems, but not studies yet. So it's easier because we have 2 information, but it's all the same solution. It's all coastal. So it's maybe easier for management to have, okay, it's on coastline, so the solution would be one solution. So I think we have not the same problem for adaptation, but we will have, because we have some rivers on coastline. So we will have, but we are not there yet.
Yeah, but there's of course also the aspect of the type of dike or coastal protection you build also affects the type of wave and how it breaks. So there are still aspects related to really local assets there.
Yeah, engineering solution can be quite different.
Yeah.
Might have time for one final question you can squeeze.
Mhm.
I have a nerdy question. So your cupola plots, what did you use to produce them?
The colorful ones,
Yeah.
I think it says Clayton in the parentheses. Is that what you mean?
No, I mean the software that you use to produce the figures.
The software?
Yeah.
I'm still a MATLAB user. I haven't transitioned. Sorry, I get blamed all the time.
So this is all MATLAB?
Yeah,
Okay.
you can get the code if you want it. If you are still a MATLAB user also.
Yeah, for our paper we used MATLAB, but this is the only study that we use MATLAB for in the past few years. We use Python, and we only use MATLAB for this because the Copula software package for Python seemed a bit limited. But in retrospect, I think that was a mistake. I think we should have just switched.
Okay, but I'm happy to share the code if you want. There's one more question I can see.
Yeah, Luis, you can go.
Yeah, sorry, it's maybe a bit less interesting after your question, Louis-Philippe, but thanks for the presentation. It was exactly about this graphic. That's why I thought I would ask now. I was just wondering on the bottom right graphic, so RCP 8.5, what's the physical explanation for the line going down towards the -50 water level there? I was just curious about that.
Yeah, so I mean that's if the more artificial data points I produce, the cleaner these ESO lines look. So it was just a matter of computation time. So I think maybe this is based on 500,000 realizations. So if I had produced 10 times that amount, it would have a really clean shape. So it's just not so data heavy right in that area.
Okay, I understand.
Which is of course also an effect of the original data that didn't have a lot of data there. So that's like a
interesting. Thank you.
Yeah.
Okay. Well, I think that'll be it. We're out of time. So just want to thank you again, Martin, for taking the time to present what's going on in Denmark. It was very interesting, anyway, for me. So thank you so much. And
thank you all. Yeah, thanks a lot.
Yeah. And then yeah, we'll let you go to your holiday.
Thanks a lot. Yeah, have a good day.
Yeah, you too. Bye-bye.
Bye-bye.